Hello there, and welcome to the Sleepy Space Channel. Tonight we are going to ask a question so close to home that it is almost embarrassing to admit we have never thought to ask it carefully. What is happening inside the sun, right now, at this very moment, as you settle in for the night? The sun rose this morning. It will set tomorrow. We know its warmth on the back of a hand. We know the way a room fills with its light in the late afternoon. We know it as a presence rather than a place, a source of warmth and daylight that we have lived beside our entire lives without ever really asking what it is doing while we are not looking. And the answer, as it turns out, is one of the most extraordinary things in all of science. A particle of light created at the absolute center of the sun right now will spend, depending on how the calculation is made, somewhere between 10,000 and 100,000 years simply trying to reach the surface. It bounces, it scatters, it is absorbed and re-emitted and absorbed again, in a wandering, purposeless journey through a medium so dense and so opaque that progress outward is nearly impossible. And then, having finally escaped to the visible surface, that same particle of light crosses the 150 million kilometers between the sun and the earth in 8 minutes and 20 seconds. The warmth on your face tomorrow morning, the light that will reach your window at dawn, was born in nuclear fire somewhere between 10,000 and 100,000 years ago. While human beings were learning to make tools and paint on cave walls and cross land bridges between continents, the photons that will warm their descendants were still buried inside the sun, inching their way toward the surface. Tonight, we will follow that journey. We will begin in the very center of the sun, where temperatures reach 15 million degrees and where the pressure is 250 billion times greater than the air pressing against your skin right now. We will move slowly outward through the radiative zone, through the mysterious and consequential boundary layer called the tachocline, into the rolling, churning convective zone where enormous columns of plasma rise and fall in a constant cycle that has continued without pause for 4.6 billion years. We will arrive at the visible surface, the photosphere, and step outward from there into the chromosphere and the corona, where temperatures climb paradoxically back to millions of degrees in a way that has puzzled scientists for 80 years. And we will close with an honest account of what is still unknown, what the best instruments ever built are, right now, in the same sense that the sun is right now, working to understand. Over the next 2 hours and 15 minutes, we will walk through all of this, unhurried, without urgency, stopping wherever the picture is worth dwelling in. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here, but for the next 2 hours and 15 minutes, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. The core, where energy is born. There is a point at the center of the sun where nothing in the known universe, except perhaps the first moments after the Big Bang, has ever been hotter. That point is the solar core, and it occupies roughly the innermost 25% of the sun's radius. Its outer boundary lies about 174,000 kilometers from the center, a distance roughly equal to half the distance between the Earth and the Moon. Within that region, conditions so extreme that they have no analogy in ordinary experience are maintained, continuously, right now, as you lie in the dark listening to these words. To understand what is happening in the core, the first thing to let go of is the word burning. The sun does not burn. It does not combust in the chemical sense that a candle burns or a piece of coal catches flame. Those are processes of oxidation, electrons rearranging themselves around atoms in ways that release the energy stored in chemical bonds. The sun is doing something far older and far deeper. It is fusing atomic nuclei together. It is pressing matter so tightly, under such tremendous heat, that the fundamental forces governing the interior of atoms themselves become relevant. And it is at this level, the level of the atomic nucleus, that the sun's energy is produced. The temperature at the core is approximately 15 million degrees Celsius. This number sits so far outside ordinary experience that it is difficult to anchor it to anything meaningful. Consider, as a starting point, that the surface of the Sun, which we experience from 150 million kilometers away as something so intensely bright that looking directly at it damages the human eye, has a temperature of about 5,778 Kelvin, which is roughly 5,500 degrees Celsius. The core is nearly 3,000 times hotter than that. At 15 million degrees, matter does not exist in any form that has a name in everyday language. There are no atoms in the conventional sense, because every electron in the core has been stripped away from its nucleus by the thermal energy of the surrounding plasma. What remains is a soup of bare nuclei, hydrogen nuclei, which are single protons, and the helium nuclei being produced by fusion, and a sea of free electrons, all moving at velocities that would be incomprehensible in any other context. A proton in the solar core is moving on average at roughly 700 kilometers per second, 700 kilometers every second. Not kilometers per hour, as one might quote for a fast aircraft, but kilometers per second. In 1 second, such a proton would travel from the Earth's surface to a point beyond the stratosphere, beyond the mesosphere, far into the thermosphere, and then back, nearly twice. The protons in the solar core are moving at that speed continuously and colliding at that speed constantly, and it is the consequence of those collisions, the quantum mechanical consequences, as we will see, that produces every joule of energy the Sun has ever released. The pressure at the core is approximately 250 billion atmospheres. A single atmosphere is the pressure exerted by the full weight of the Earth's atmosphere above a single square centimeter of the surface. You do not notice it because your body is built to balance it. 250 billion of those atmospheres is a pressure produced by the gravitational weight of the entire mass of the Sun, bearing inward toward the center. The Sun contains approximately 2 times 10 to the power of 30 kilograms of matter, about 330,000 times the mass of the Earth. And all of that mass is, at every moment, being pulled toward the center by gravity. In the core, the pressure generated by this infall is balanced only by the outward pressure of the energy being released by nuclear reactions. The Sun is in a state of equilibrium between gravity and radiation that has been maintained for 6 billion years, and that will continue for approximately another 5 billion years. It is the most enduring balance in the solar system. Sit for a moment with the picture of that equilibrium. Gravity pulling inward with the weight of 330,000 Earths. Radiation pushing outward from nuclear fire at 15 million degrees. Both perfectly, continuously balanced. Not by design, not by mechanism, but by physics. Operating at the quantum level, in a region no probe will ever visit. The specific process by which the Sun produces its energy is called the proton-proton chain, a sequence of nuclear reactions worked out in complete quantitative detail by Hans Bethe, a physicist at Cornell University, in 1938. Bethe's paper, published in the journal Physical Review, was one of the foundational achievements of 20th century astrophysics, and it earned him the Nobel Prize in Physics in 1967. Understanding what Bethe worked out requires first understanding why fusion is so difficult, and why it happens in the Sun's core despite being impossible at ordinary temperatures. 2 protons, 2 bare hydrogen nuclei, each carrying a positive electric charge, repel each other electromagnetically, like charges repel. The Coulomb barrier, as this repulsion is called, prevents protons from approaching each other closely enough for the strong nuclear force, the force that binds nuclei together, to take over. At ordinary temperatures, protons simply bounce off each other. But at 15 million degrees, something else becomes possible. Quantum mechanics, the physics that governs the behavior of matter at the subatomic scale, permits a phenomenon called tunneling. A particle does not always behave like a classical billiard ball bouncing off a wall. Quantum mechanically, a particle can pass through a barrier that it classically lacks the energy to surmount, with a probability that depends on the height and width of the barrier and the mass and energy of the particle. This is not a metaphor or a loose analogy. Quantum tunneling is among the most experimentally confirmed phenomena in all of physics. It is the principle behind the tunnel diode, the scanning tunneling microscope, and several other technologies. And in the solar core, at 15 million degrees, it is the mechanism by which fusion happens. The probability of tunneling for any given pair of protons, in any given collision, is extraordinarily small. A specific pair of protons in the solar core must wait, on average, several billion years before they tunnel through the Coulomb barrier and fuse. Several billion years, longer than the Earth has existed, for a single pair of protons. What makes the Sun's fusion rate enormous, despite this extraordinarily small per-pair probability, is the sheer number of protons involved. The solar core contains roughly 10 to the power of 57 protons. When a process with a tiny probability per event occurs among 10 to the 57th participants, the total event rate can still be stupendously large. When two protons do tunnel and fuse, one of them undergoes inverse beta decay, a weak nuclear process in which a proton converts to a neutron, emitting a positron, the antimatter counterpart of the electron, and a neutrino. What remains is a deuteron, the nucleus of deuterium, or heavy hydrogen, containing one proton and one neutron bound together by the strong force. This first step, the fusion of two protons into a deuteron, is the slowest and most rate-limiting step in the entire chain. It is the bottleneck. Everything else that follows happens relatively quickly. The deuteron then fuses with another proton, very quickly by comparison, in a matter of seconds, not billions of years, producing helium-3, a nucleus with two protons and one neutron. This reaction releases a gamma ray, a photon of very high energy that immediately begins its own long journey through the solar interior. And then two helium-3 nuclei fuse to form helium-4, ordinary helium, with two protons and two neutrons, the second most abundant element in the universe, releasing two protons that re-enter the cycle as fresh participants. The net result of the full chain, 4 hydrogen nuclei have been converted into one helium-4 nucleus. The critical fact in that transformation is this: the helium-4 nucleus has slightly less mass than the 4 hydrogen nuclei it was made from. The missing mass, approximately 0.7% of the original, has been converted into energy according to Einstein's relation E equals mc squared. That fraction, 0.7%, sounds small. But the speed of light squared is an enormous number, approximately 9 times 10 to the power of 16 meters squared per second squared. And the mass of even a tiny amount of hydrogen is many kilograms. The result is an energy release per reaction that makes every chemical reaction in known chemistry look trivial. The Sun converts approximately 620 million metric tons of hydrogen into helium every second. Of that, roughly 4.3 million metric tons per second are converted directly into pure energy. The rest becomes helium, 4 million tons per second, converted into energy per second for 4.6 billion years and for another 5 billion years to come. There is something worth staying with here. The warmth on your skin, the light in your window, the energy that drives every weather pattern, every ocean current, every photosynthesis reaction on Earth. All of it is the product of 4 million tons of matter ceasing to exist as matter every second. The Sun is, in the most literal possible sense, consuming itself. It is slightly less massive today than it was yesterday. It will be slightly less massive tomorrow. Over the course of its 10 billion year lifetime, it will have lost approximately 3% of its original mass in this way. The energy released by the proton-proton chain takes several forms. Part of it becomes the kinetic energy of the newly created helium nucleus and the released protons, which heat the surrounding plasma. Part of it becomes the gamma-ray photons emitted during the fusion reactions. And part of it, a significant fraction, roughly 2% of the total, is carried away by neutrinos. Neutrinos deserve a patient explanation because they are among the strangest and most informative messengers in all of physics. They have almost no mass. The current best upper limit on the electron-neutrino mass is approximately 0.8 electron volts, compared to the electron's mass of approximately 511,000 electron volts. And they carry no electric charge. They interact with ordinary matter only through the weak nuclear force, which operates only at ranges shorter than about 10 to the minus 18 meters, roughly 1% of the diameter of a proton. In practical terms, this means that a neutrino will pass through almost any amount of ordinary matter without interacting. If you wish to stop a solar neutrino with a 50-50 probability, you would need a wall of solid lead approximately 1 light-year thick. Approximately 65 billion solar neutrinos pass through every square centimeter of your body every second, day, and night, regardless of whether the sun is above or below the horizon, regardless of whether you are in the basement or on a hilltop. They pass through the Earth as if it were not there. They pass through you as if you were not there. They leave the solar core, where they were produced, at essentially the speed of light, and they arrive at Earth 8 minutes and 20 seconds later, carrying direct information about the state of the solar core at that moment. The neutrinos arriving at Earth right now carry news of fusion reactions that happened 8 minutes ago. The light arriving at Earth right now was produced in the photosphere from energy that left the core somewhere between 10,000 and 100,000 years ago. In this sense, neutrinos are a faster and more direct window into the sun's current interior than any other signal we can receive. Every other observation of the sun, its light, its spectrum, its surface oscillations, tells us about what the sun is doing near its surface, or about interior conditions as reflected indirectly by long-delayed processes. Neutrinos tell us about the core right now. The history of solar neutrino detection is one of the great stories in 20th century physics, and it deserves a quiet retelling. Beginning in the 1960s, Raymond Davis Jr., a chemist at Brookhaven National Laboratory working at a detector deep inside a gold mine in Lead, South Dakota, the Homestake Mine, nearly 1,500 meters underground, shielded from cosmic rays by rock, began counting solar neutrinos. His detector was a tank containing approximately 380,000 liters of perchloroethylene, a common dry cleaning fluid, in which the rare interaction of an electron neutrino with a chlorine atom would produce a radioactive argon atom. By periodically purging the tank and counting argon atoms, Davis could estimate the neutrino flux from the sun. The result was puzzling. Davis was detecting, consistently, only about 1/3 of the neutrinos that the theoretical models predicted. John Bacall, a physicist at the Institute for Advanced Study in Princeton, had developed the solar models against which the observations were compared, and he refined them repeatedly over the following decades. The models kept predicting 3 times as many neutrinos as Davis found. Either the models of the solar core were wrong, or the neutrinos themselves were doing something unexpected. The resolution came in 2001 and 2002 from the Sudbury Neutrino Observatory in Ontario, Canada, a detector buried 2 kilometers underground in a nickel mine, using 1,000 tons of heavy water as its detection medium. Sudbury was capable of detecting all 3 types of neutrinos, electron, muon, and tau, rather than just electron neutrinos. When all 3 were counted together, the total matched Bacall's solar models precisely. The missing neutrinos had not disappeared. They had changed type. Electron neutrinos produced in the solar core had oscillated into muon and tau neutrinos during their journey to Earth, in a quantum mechanical process called neutrino oscillation that could not happen if neutrinos had 0 mass. Davis's detector, sensitive only to electron neutrinos, had been counting only the ones that had not yet oscillated. The solar neutrino problem was resolved. The sun was doing exactly what the models said, and neutrino physics was permanently changed. Neutrino oscillation is now established science, and the discovery has implications across particle physics and cosmology that are still being worked through. Davis received the Nobel Prize in Physics in 2002 for his pioneering work on neutrino detection. Bacall, who had maintained through decades of doubt that the solar models were correct, did not receive the prize. He died in 2005. His models were vindicated. The sun had been telling the truth all along. Let your breathing slow for a moment. Let the core rest as it is. 15 million degrees, 250 billion atmospheres, 4 million tons of matter becoming energy every second. Neutrinos streaming outward at light speed, carrying news 8 minutes old from the center of the star you orbit. None of this asks anything of you tonight. It is simply what is happening right now in the sun. There is one more picture from the solar core that deserves an unhurried moment before we move outward. The energy density in the core, the amount of energy released per cubic meter per second, is, paradoxically, quite modest. A cubic meter of solar core plasma releases roughly as much energy per second as a cubic meter of active compost heap. The sun produces its staggering total luminosity not through any extraordinary energy density in individual cubic meters, but through the vast size of the core. A volume so enormous that even a modest energy release per unit volume multiplies to an output of approximately 3.828 times 10 to the 26th power watts. That number, written out in full, requires 27 digits. Per second, the sun releases more energy than humanity has generated in its entire industrial history. This contrast between the mundane energy density per cubic meter and the staggering total output reflects something important about how the sun works. It does not burn fiercely at any one point. It burns slowly and patiently across an incomprehensibly large volume for an incomprehensibly long time. This is why a given proton waits billions of years before fusing. The system is in no hurry. The sun has approximately 5 billion years of hydrogen remaining in its core. It does not need to rush. The solar core also carries a direct record of the sun's evolutionary history. As hydrogen is converted to helium, the helium gradually accumulates. A helium nucleus has more mass than 4 protons, slightly less than the sum of 4 protons by the fraction converted to energy, but still more massive than a single proton. As helium accumulates in the core, the mean molecular weight of the core plasma rises slowly. A higher mean molecular weight requires a higher temperature to maintain the same pressure needed to balance gravity. A higher temperature means faster fusion reactions and higher luminosity. This is why the sun today is approximately 30% more luminous than it was when it first formed 4.6 billion years ago. And it is why the sun will be roughly 10% brighter still in about 1 billion years. Bright enough that Earth's surface temperatures will have risen significantly, presenting the long-term challenge to life on this planet that comes not from any catastrophe, but from the quiet, patient physics of stellar evolution. In approximately 5 billion years, the hydrogen in the core will be exhausted. The sun will then begin fusing hydrogen in a shell surrounding the now helium core, causing the outer layers to expand enormously. The sun will become a red giant, swelling to perhaps 150 times its current radius, engulfing Mercury and Venus, and possibly reaching the orbit of Earth. The outer layers will eventually be shed as a planetary nebula, a glowing shell of gas expanding outward into interstellar space, briefly illuminated by the ultraviolet radiation of the exposed stellar core. What remains will cool slowly over billions of years as a white dwarf, a dense, Earth-sized remnant, composed primarily of carbon and oxygen, glowing by residual heat with no ongoing fusion. In perhaps 100 billion years, longer than the current age of the universe, it will have faded to a cold, dark cinder. All of this is the future of what is happening right now in the solar core. The proton-proton chain burning at 15 million degrees, the slow accumulation of helium, the gradual rise in luminosity. These are the first acts of a story that will end, after 10 billion years, in a white dwarf drifting silently through what will then be a very old and very quiet galaxy. Let that picture rest where it is. Tonight, the sun is in the middle of its story. It is burning steadily, as it has for 4.6 billion years. That is more than enough to consider for one quiet evening. The radiative zone. The 100,000-year journey. Moving outward from the core, through the inner 25% of the sun's radius, the density and temperature gradually decrease, and we enter the radiative zone, a vast shell of plasma extending from the outer boundary of the core at about 174,000 kilometers from the center to roughly 70% of the Sun's radius at approximately 487,000 kilometers. The radiative zone occupies a huge volume, a thick shell of plasma roughly 313,000 kilometers deep, sitting between the nuclear furnace of the core and the turbulent convective zone above. It is through this region that the energy produced in the core must travel to reach the surface. The name, radiative zone, tells you how energy moves through it, by radiation, which in this context means the transport of energy by photons. But the photon's journey through the radiative zone is nothing like the clean, swift passage of light through air or vacuum. It is one of the most indirect and impeded journeys in all of nature. A photon traveling through the radiative zone travels in a straight line only until it encounters a particle, which it does almost immediately. In the inner regions of the radiative zone, the mean free path of a photon, the average distance between one absorption event and the next, is approximately 1 centimeter. A single centimeter. The inner radiative zone is more than 300,000 kilometers across, and each step of the photon's journey through it is 1 centimeter long. After each absorption, the photon is re-emitted in a direction chosen essentially at random. It might proceed outward, toward the surface. It might proceed inward, back toward the core. It might go sideways. There is no preference for any direction. The path that results, a long series of random steps, each 1 centimeter long in a completely random direction, is called a random walk, and it is one of the fundamental concepts of statistical physics. The random walk describes the motion of a dust particle jostled by molecules in air, or a molecule diffusing through a liquid, or a drunk person wandering home with no memory of which direction home is. The photon in the radiative zone is doing exactly this, except that its home, the solar surface, is 300,000 kilometers away, and each step is 1 centimeter. To understand why this matters, consider a slightly simplified version of the mathematics. In a random walk on a line, the average distance from the starting point after n steps of length L is approximately the square root of n times L. To cross a distance d in steps of length L requires approximately d squared divided by L squared steps. Applying this to the radiative zone, distance d is 300,000 kilometers, or 3 times 10 to the 10th centimeters. Step length L is 1 centimeter. The number of steps required is approximately 9 times 10 to the 20th. 900 billion steps, each 1 centimeter long. At the speed of light, 30 billion centimeters per second, those steps would take approximately 30,000 years. That estimate assumes pure random walk without any bias. More detailed models of the solar interior, accounting for the actual density and opacity profile and the slight tendency of radiation pressure to push photons outward, give estimates ranging from about 10,000 years at the low end to about 100,000 years at the high end. Different researchers using different models get different answers within this range, and the honest answer is that the precise value is still being refined through improvements in our understanding of plasma opacity. But the order of magnitude, tens of thousands of years, is not in serious dispute. It is worth giving the listener a few unhurried sentences to settle into what this means. The light that is warming the Earth today, the light that is, right now, maintaining the ocean temperatures and atmospheric circulation patterns and photosynthesis reactions that make your life possible, was created in nuclear reactions that occurred somewhere between 10,000 and 100,000 years ago. The photons carrying that energy spent the entire span of human prehistory crawling through the radiative zone, while the first behaviorally modern humans were crossing into Australia, while Neanderthals still walked the Earth. While ice ages came and went and sea levels rose and fell by hundreds of meters, the photons that would one day warm a 21st century human lying in the dark were still deep inside the sun, bouncing through an opaque wall of plasma, 1 centimeter at a time. The energy released in the core right now, in the fusion reactions happening at this very moment, will not warm the Earth until somewhere between the year 12,000 CCE and the year 102,000 CE. Whatever civilization exists then will be warmed by the sun's present exertions. We will never know if anyone will be there to receive it. Something in this deserves to rest in mind without urgency. The density of the radiative zone decreases continuously as you move outward from roughly 150 grams per cubic centimeter at the inner boundary, about 10 times denser than lead, 15 times denser than copper, about 50 times denser than bone, to roughly 20 grams per cubic centimeter at the outer boundary. Lead has a density of about 11 grams per cubic centimeter. The inner radiative zone is more than 10 times denser than lead, yet it is not a solid, not a liquid, not a conventional gas. It is a plasma, its particles held in place by nothing more than the balance between gravity, pressure, and radiation. There are no walls, no containers, no surfaces. There is only the physics of a hot, dense ionized gas under enormous gravitational pressure. The opacity, the resistance of the plasma to the passage of photons, is one of the most important quantities in stellar physics, and understanding it has been a major focus of solar physics for a century. Opacity depends on the temperature, density, and chemical composition of the plasma, and it determines how much of the radiative zone a photon can expect to traverse before being absorbed. Cecilia Payne-Gaposchkin, working at Harvard College Observatory in the 1920s, was the first scientist to demonstrate conclusively that stars are composed primarily of hydrogen and helium rather than the heavier elements that dominate the solid, rocky planet we live on. Her doctoral thesis, completed in 1925 and described by the astronomer Otto Struve as the most brilliant PhD thesis ever written in astronomy, showed through careful analysis of stellar spectra that the ratios of spectral line strengths could be explained by a composition of roughly 73% hydrogen by mass and approximately 25% helium, with heavier elements forming only the remaining 2%. This result was initially doubted. The idea that the sun was overwhelmingly made of the lightest elements seemed counterintuitive and was dismissed by some of her contemporaries. It was later confirmed beyond question and is now a cornerstone of solar and stellar physics. The heavier elements in the sun, oxygen, carbon, nitrogen, neon, iron, despite constituting only about 2% of the mass, contribute disproportionately to the opacity of the plasma, because their more complex electron structures offer far more opportunities for photon absorption than the bare protons and alpha particles of hydrogen and helium. This 2%, the ashes of previous generations of stars whose supernovae seeded the interstellar medium before the sun formed, affects the behavior of every photon trying to escape the solar interior. As photons make their long random walk outward through the radiative zone, something else is happening to them that is worth patient attention. A photon born in a fusion reaction in the core is a gamma ray. A photon of extremely high energy, with a wavelength far shorter than the X-rays used in medical imaging, far shorter than ultraviolet light, far shorter than visible light. The wavelength of a solar core gamma ray is on the order of 10 to the minus 12 meters, about 1,000th of the diameter of a hydrogen atom. But each time such a photon is absorbed by an ion and re-emitted, there is no requirement that the re-emitted photon have exactly the same energy as the absorbed one. The energy can be redistributed. A single high-energy photon absorbed by a hot ion can emerge as two lower-energy photons going in different directions. Or the energy can be deposited into the thermal motion of the ion, slightly raising the local temperature, and then re-emitted as a photon of slightly different energy. Over the course of tens of thousands of years, and an incomprehensible number of absorption-emission events, the characteristic energy of photons gradually decreases as they move toward the surface. Gamma rays in the core, X-rays in the inner radiative zone, extreme ultraviolet deeper in the zone, soft ultraviolet toward the outer edge, and finally, at the surface, the primary emission is in the visible and near-infrared, the golden, orange, warm light we see when we look at the sun. The gentleness of visible sunlight, the quality that lets us look almost though not quite directly at a sunset, is the product of this vast energetic degradation across 100,000 years and trillions of individual photon interactions. Sit for a moment with the strangeness of this. Every photon of gentle visible sunlight began as a gamma ray born in nuclear fire. The warmth of morning light is ancient energy finally and slowly arrived after a geological age of wandering. Helioseismology, the study of the sun's interior using oscillations on its surface, has given scientists a way to probe the radiative zone without entering it. The sun oscillates in millions of resonant modes simultaneously, like a struck bell resonating at many frequencies at once, but far more complex. These oscillations, measured as tiny Doppler shifts in the velocities of the sun's surface plasma, carry information about the sound speed, density, and rotation rate at every depth in the solar interior. The Solar and Heliospheric Observatory, SOHO, a joint mission of the European Space Agency and NASA launched in December 1995 and still operating, has mapped these oscillations continuously for nearly 3 decades, providing a helioseismic portrait of the solar interior with a depth and precision that would have seemed impossible to the generation that first proposed the technique. One result from helioseismology that bears directly on the structure of the radiative zone is the measurement of its rotation. The radiative zone rotates nearly as a solid body, all parts of it turning at approximately the same rate, making roughly one complete rotation every 27 days. This is strikingly different from the convective zone above it, where the equatorial regions rotate faster than the polar regions. A phenomenon called differential rotation that we will explore in the next part of tonight's exploration. The boundary between these two different rotation regimes is thin, occupying only a few % of the sun's radius, and it is one of the most scientifically consequential layers in the solar interior. It is called the tachocline. Let the radiative zone settle in mind as what it is before we step through it. A 313,000-kilometer deep shell of plasma, ranging in density from 10 times denser than lead at its inner edge to about twice the density of lead at its outer edge. Opaque. Slowly brightening as you move outward, as gamma rays degrade to X-rays degrade to ultraviolet. Crossed by photons in a random walk lasting geological ages. Probed only indirectly, through neutrinos and helioseismology, by instruments on a planet 150 million kilometers away. Patient, ancient, dark. The numbers do not need to be memorized. The point is only that the journey through the radiative zone is one of the great slow facts of nature, 100,000 years of diffusion, holding the energy of nuclear fire back from the cold of space, releasing it grain by grain. The study of how light interacts with the solar plasma, the science of opacity, is itself a rich and technically demanding field. The opacity of a gas depends on the probabilities of all the various interactions between photons and the particles around them. Photoionization, in which a photon is absorbed and liberates an electron from an ion. Free absorption, in which a photon is absorbed by a free electron passing near an ion, and scattering by free electrons. Each of these processes has a probability that depends on the photon's energy and the local temperature and density. Calculating the total opacity of the solar plasma and its variation with depth requires tracking all of these processes for all of the different atomic species present, across a very wide range of temperatures and densities. This is a problem that required decades of careful laboratory measurements, theoretical calculations, and the development of computer codes capable of handling millions of atomic transitions simultaneously before reliable opacity tables for stellar interiors could be produced. The Lawrence Livermore National Laboratory in California and the Opacity Project, an international collaboration of atomic physicists and astrophysicists, have been among the institutions most deeply involved in producing the opacity calculations used in modern solar models. Their work is not glamorous. It involves tabulating the behavior of ions of iron, nickel, oxygen, and carbon at extreme conditions, comparing theoretical predictions with laboratory measurements, and iterating until the results are consistent. But it is foundational. Every model of the solar interior, every helioseismic inversion that tells us about the sun's internal structure, depends on accurate opacity tables. The solar abundance problem mentioned earlier, the discrepancy between spectroscopic and helioseismic determinations of the sun's composition, may partly be a consequence of remaining uncertainties in opacity calculations. Ongoing work to measure opacities in laboratory plasmas at conditions closer to those in the solar interior is one of the paths toward resolving this long-standing puzzle. Helioseismology has been the other great observational tool for the radiative zone. The principle is elegant. Sound waves propagating through the solar interior are refracted by temperature and density gradients, and they eventually return to the surface where they produce tiny oscillations in the Doppler velocity of the plasma. By measuring these oscillations across the entire solar disk, simultaneously and continuously, and decomposing them into their component frequencies and spatial modes, it is possible to invert the observations and reconstruct the sound speed and density at each depth in the interior. The technique was pioneered in the 1970s and 1980s and reached maturity with the SOHO mission in the mid-1990s. One of the most striking results from helioseismology, and one directly relevant to the radiative zone, is how precisely the observed oscillation frequencies match the predictions of solar models. The agreement between theory and observation is at the level of a fraction of a percent throughout most of the solar interior. This agreement is the foundation of our confidence that the basic picture of the radiative zone is correct, that it really is a region of outward radiation transport, that its density and temperature profiles are roughly as calculated, and that the photon random walk through it really does take the tens of thousands of years the models predict. The physics of the solar interior, strange and remote as it is, has been tested against observation and confirmed. There is something reassuring in this, if reassurance is appropriate. The account of the radiative zone given here tonight is not speculation. It is the product of a century of careful work by physicists and astronomers, tested against the best observations available, confirmed at the level of precision that modern instruments allow. The picture is genuine. The 100,000-year journey is real. The sun also vibrates in what are called gravity modes, or G modes, oscillations in which the restoring force is buoyancy rather than pressure, concentrated in the deep interior where the radiative zone is stably stratified. G modes, if detected and characterized, would provide the most direct probe of the solar core available by any observational technique other than neutrinos. Because these waves live primarily in the core, they would reveal the rotation rate and structure of the deep interior with a precision that pressure mode helioseismology cannot match. A claimed detection of solar G modes published in 2017 using decades of SOHO data attracted significant attention but has not been confirmed by independent analysis and remains disputed. The search continues. If G modes are eventually detected unambiguously, the interior portrait of the sun will become sharper in ways that matter for every model of stellar evolution that depends on it. There is something in this ongoing search. Patient, careful, technically demanding, aimed at a signal buried in data that has been accumulating for decades. That reflects the broader character of solar science. The sun has had instruments pointed at it continuously for longer than any other astronomical object, and it still holds secrets. The tachocline and the convective zone. At approximately 70% of the sun's radius, about 487,000 kilometers from the center, a transition occurs that changes everything about how energy is moved, how the magnetic field is generated, and how the sun's dramatic surface behavior is ultimately produced. The radiative zone ends. Convection begins, and between them, occupying a layer only a few percent of the sun's radius thick, lies one of the most consequential and most difficult to observe structures in the solar interior. The tachocline. The word tachocline was coined in 1992 by the solar physicists Edward Spiegel and Jean-Paul Zahn, and it refers to a zone of shear, a layer where two regions of the sun rotating at very different rates meet and produce intense relative motion between adjacent layers of plasma. Below the tachocline, in the radiative zone, the sun rotates nearly rigidly, like a solid ball, with all parts turning at the same rate. Above the tachocline, in the convective zone, the sun rotates differentially. The equatorial regions complete one rotation in about 25 days, while the polar regions take about 35 days. These two very different behaviors must transition somewhere, and the transition is the tachocline. Wherever electrically conducting plasma flows are sheared across each other, the conditions are right for the generation of magnetic fields by a dynamo process. The tachocline is widely believed to be the primary seat of the solar dynamo, the mechanism by which the sun's large-scale magnetic field is generated and maintained. The fundamental idea is that the shear in the tachocline stretches and amplifies magnetic field lines, winding them up into intensified toroidal structures that eventually become buoyant and rise through the convective zone, emerging at the surface as sunspots and active regions. The details of exactly how this works, how the field is amplified, how it is organized into the patterns we see at the surface, how the cycle reverses every 11 years, are among the most actively studied problems in solar physics, and a complete quantitative model of the solar dynamo does not yet exist. Subrahmanyan Chandrasekhar, the Nobel Prize-winning astrophysicist at the University of Chicago who made fundamental contributions to stellar structure, hydrodynamic stability, and the physics of magnetic fields in plasma across more than 6 decades of scientific work, receiving the Nobel in 1983 for his work on the theory of stellar evolution, and particularly his discovery of the Chandrasekhar limit on white dwarf mass, laid some of the mathematical groundwork for magnetohydrodynamic theory that informs modern dynamo models. The problem of the solar dynamo as a whole, though, remains incompletely solved. What is not in any serious doubt is that the magnetic field originating in and around the tachocline is responsible for essentially all of the sun's most dramatic and visible behavior. Sunspots, solar flares, coronal mass ejections, prominences, filaments. The 11-year cycle of solar activity. Trace each of these back to its cause, and you arrive at the tachocline. The most hidden layer in the sun produces the most visible behavior on its surface. There is something characteristic of physics in this observation. The most important processes are often the most inaccessible. The tachocline has never been directly observed. No spacecraft has ever entered the sun, and even if one could, the tachocline lies nearly 500,000 kilometers below the visible surface. Its existence was inferred from helioseismology. Its properties are still being refined. Its full role in the solar dynamo is still being debated. And yet, without it, the sun's surface would be a quiet, uniform, featureless disk of plasma. None of the drama, none of the activity, none of the magnetic complexity that makes the sun so scientifically interesting and, in practical terms, so important to understand for space weather forecasting. Let that thought rest quietly before we step upward into the convective zone. The convective zone extends from the tachocline, at 70% of the sun's radius, outward to the visible surface, a shell about 200,000 kilometers deep, encompassing the outermost 30% of the sun's radius. In this region, a crucial change has occurred. The plasma has become cool enough, in relative terms, being only 1,000,000 degrees or so at the tachocline, cooling to about 5,778 Kelvin at the surface, that the opacity of the material has increased sharply. The plasma can no longer efficiently transport energy outward by radiation alone. The photon mean free path has not increased enough to allow radiation to carry the full energy flux. Instead, the plasma becomes convectively unstable. Convection is, in some ways, the most familiar process in this entire story. It is what happens when you heat the bottom of a pot of water. Hot fluid rises because it is less dense than the surrounding cooler fluid. It carries its thermal energy upward with it. When it reaches the surface, it radiates that energy away, cools, becomes denser, and sinks back down. This process, The physical transport of thermal energy by bulk motion of the fluid itself is convection. You have seen it in every pot you have ever put on a stove. You have felt it in the way warm air rises from a heater. It is, in the most literal sense, ordinary. In the sun, this ordinary process operates at a scale and intensity that leave ordinary experience far behind. The convective zone is roughly 200,000 kilometers deep. The material flowing within it reaches temperatures between about 1 million degrees at the tachocline and 5,778 Kelvin at the photosphere. The velocities of the ascending and descending columns of plasma are hundreds of meters per second. The magnetic field threading through the convective zone is constantly being tangled, stretched, amplified, and reorganized by these motions. And the visible manifestation of all this convective activity, the surface texture we can observe with appropriate instruments, is one of the most beautiful and instructive features of the solar surface. The most visible manifestation of solar convection is the granulation pattern on the sun's photosphere. When observed with a high-resolution solar telescope, such as the instruments aboard the Hinode satellite, a joint mission of the Japan Aerospace Exploration Agency, NASA, and the European Space Agency, launched in September 2006, the sun's surface appears as a constantly shifting mosaic of roughly polygonal bright regions separated by darker lanes. Each bright region is a granule, a convection cell in which hot plasma rises from below, spreads outward across the surface, radiates energy into space, cools, and sinks back down along the narrow dark lanes at the edges. The dark lanes are the cool descending plasma. The bright regions are the hot ascending plasma. A typical granule is about 1,000 kilometers across, roughly the size of Texas, or about 1/8 the diameter of the Earth. The granules appear and disappear on timescales of about 5 to 10 minutes, as new columns of hot plasma rise and old columns cool and sink. Watching a time-lapse of the solar granulation, as the Solar Dynamics Observatory, NASA's solar observing satellite launched in February 2010, has provided in extraordinary detail, is like watching the surface of a pot of something thick and slow boiling at extraordinary speed, except that each bubble is the size of Texas and the boiling is happening at 5,778 Kelvin. At any moment, the sun's surface is covered in approximately 4 million granules. 4 million continent-sized convection cells, all rising and sinking and disappearing and reforming simultaneously, continuously, as they have been for 4.6 billion years. The numbers do not need to hold precise meaning tonight. What matters is the picture. A surface in constant, gentle, enormous motion, covered in continent-sized rising and sinking structures, each one maintaining the flow of energy from the sun's interior to the cold of interplanetary space. At larger scales, the solar surface shows a second tier of convective structure that is somewhat more mysterious. These are called supergranules, convection cells roughly 30 times larger than ordinary granules, about 30,000 kilometers across, with lifetimes of 1 to 2 days rather than minutes. Unlike ordinary granules, supergranules are defined primarily by horizontal flows rather than vertical ones. Plasma within a supergranule moves outward from its center to its edges more than it moves vertically, sweeping magnetic field lines along with it into the narrow corridors between supergranules. The origin and exact dynamics of supergranulation are still subjects of research. They are detectable by helioseismology and by Doppler measurements of surface velocities, but their relationship to the convective motions deeper in the convective zone is incompletely understood. At even larger scales, convective structures called giant cells are predicted by models of the convective zone, structures hundreds of thousands of kilometers across, organized by the Coriolis force that arises from the sun's rotation, and playing an important role in the transport of angular momentum and magnetic field through the convective zone. Their existence has been difficult to confirm observationally, and their properties remain debated. This is an ongoing frontier of solar interior research. The convective zone is also the region where the sun's differential rotation, faster at the equator, slower at the poles, is maintained. This differential rotation is produced by the interplay of convection and rotation. The Coriolis force, which deflects moving fluid in a rotating system, organizes convective motions in ways that transport angular momentum toward the equator, spinning it up relative to the poles. Understanding the precise mechanism by which the Sun's differential rotation profile is established and maintained is another area of active solar physics research. Helioseismology has mapped the rotation profile throughout the convective zone and has found it to be more complex than simple models predict, with structures called torsional oscillations, bands of slightly faster and slower rotation that migrate from mid-latitudes toward the equator over the course of the solar cycle. The convective zone is, in summary, a 200,000-kilometer deep shell of churning plasma, transporting the Sun's internal heat outward by bulk motion, organizing the Sun's magnetic field, maintaining the Sun's differential rotation, and covering its surface in a constantly renewing mosaic of granules and supergranules. All of it powered, ultimately, by the nuclear reactions in the core. All of it part of the answer to the question we asked at the beginning of this long, quiet evening. Let your breathing slow. Let the picture of the solar interior rest fully in mind before we move to the surface. The photosphere, the chromosphere, the corona, and the mystery that has puzzled solar physicists for nearly a century. The surface, the corona, and the great mystery. At the outer boundary of the convective zone, where the Sun's radius reaches approximately 696,000 kilometers, we arrive at the photosphere, the layer the word surface refers to, though it is not a solid surface in any ordinary sense. It is a thin layer of plasma, approximately 500 kilometers deep, at which the Sun transitions from being opaque to visible light to being transparent. Below the photosphere, photons are absorbed almost immediately after being emitted. Above it, photons can travel without significant absorption. They escape into space. The photosphere is therefore not a surface in the way that the Earth's crust is a surface. It is a horizon, a depth at which the Sun's interior becomes hidden from external view. The temperature at the photosphere is approximately 5,778 Kelvin, about 5,505 degrees Celsius. This is the temperature responsible for the Sun's characteristic yellow-white color, corresponding to a black-body spectrum peaked in the green-yellow portion of the visible spectrum. The fact that the Sun appears more white or slightly yellowish to human eyes, rather than distinctly green, reflects the broad peak of the spectrum and the specific sensitivity of human color vision. When all visible wavelengths are present in roughly equal abundance, the eye perceives white or near white, modified by the slight weighting toward red and yellow that the photospheric spectrum provides. The granulation pattern of the convective zone is fully visible at the photosphere. The bright tops of rising granules and the dark lanes of descending plasma are the dominant small-scale texture of the solar surface. But the most dramatic feature visible in the photosphere is not the granulation. It is sunspots. A sunspot is a region of the photosphere where the magnetic field, emerging from below in a concentrated bundle, is so strong that it inhibits the convection bringing heat up from the convective zone. Without convective heat transport, that patch of surface is cooler than its surroundings. A typical large sunspot is about 4,000 Kelvin, roughly 1,700 degrees cooler than the surrounding photosphere. By the Stefan-Boltzmann law, which tells us that a black body emits power proportional to the fourth power of its temperature, a surface at 4,000 Kelvin emits dramatically less light per unit area than a surface at 5,778 Kelvin. Against the intensely bright photosphere, a sunspot appears dark, though if it could be seen in isolation against a dark sky, it would be brilliantly luminous, far brighter than the full moon. The magnetic field in a large sunspot can reach strengths of several thousand Gauss, the unit of magnetic field strength. For comparison, the Earth's surface magnetic field is approximately 0.5 Gauss. The Sun's average surface field is perhaps 1 to 2 Gauss. A sunspot field is thousands of times stronger than either, concentrated into a region the size of a large country. The field is organized into a roughly vertical structure, a dark central region called the umbra, where the field is nearly vertical and convection is most completely suppressed, surrounded by a lighter region called the penumbra, where the field is more inclined and partial convection can still occur in filamentary structures called penumbral fibrils. Sunspots do not appear in isolation. They appear in pairs or groups, with opposite magnetic polarities. One spot where the magnetic field emerges from the sun's interior, the north polarity spot, and one where it dips back in, the south polarity spot. The magnetic flux tube connecting each pair stretches through the convective zone and into the tachocline below. The evolution of sunspot groups over days and weeks, as the magnetic field configuration changes, can lead to the conditions for solar flares. Sudden explosive releases of energy that we will discuss when we reach the chromosphere and corona. The number of sunspots visible at any time varies over what is called the solar cycle, an approximately 11-year period of rising and falling magnetic activity. At solar minimum, the sun's surface may be completely spotless for days or weeks at a time. At solar maximum, dozens of sunspot groups may be visible simultaneously. Active regions may span hundreds of thousands of kilometers across the disk, and the probability of major solar flares and coronal mass ejections is substantially elevated. The cycle is driven by the winding and unwinding of the sun's internal magnetic field under differential rotation. At the end of each cycle, the sun's global magnetic field reverses polarity. The north magnetic pole becomes the south and vice versa, and a new cycle begins. A complete magnetic cycle, including the polarity reversal and return, therefore takes approximately 22 years, though the visible sunspot cycle with its 11-year period is more commonly discussed. We are currently in solar cycle 25, which began in December 2019. Its behavior has, in fact, exceeded predictions. Solar activity has been higher and more sustained than the forecast, with a solar maximum arriving earlier and more energetically than models suggested. Solar Cycle 25 is a reminder that despite decades of careful observation and sophisticated modeling, the precise behavior of any individual solar cycle remains difficult to predict. The solar dynamo operates on timescales and at spatial scales that are difficult to observe directly, and its long-term behavior carries variability whose deeper causes are not fully understood. Above the photosphere lies the chromosphere, the sun's lower atmosphere, extending from the photosphere to roughly 2,000 kilometers above it. The chromosphere is best seen at the limb of the sun during a total solar eclipse, when it appears as a thin pinkish-red arc around the moon's shadow. The color produced by hydrogen's characteristic emission line, called hydrogen alpha, at a wavelength of 656 nanometers in the red portion of the spectrum. The chromosphere is hotter than the top of the photosphere. Temperatures rise from about 4,000 Kelvin at its base to approximately 20,000 Kelvin at its upper boundary. This temperature increase is already a hint of something unusual. Moving away from the sun's primary energy source should, by intuitive expectation, mean falling temperature. The fact that it rises is a foreshadowing of the much larger mystery above. The chromosphere contains beautiful and dynamic structures, spicules, which are narrow jets of plasma shooting upward from the photosphere at speeds of tens of kilometers per second, forming a constant forest of fine structure that covers the chromosphere at any given moment. Prominences, large, looping structures of cool, dense plasma suspended against the chromospheric background by magnetic field lines, are visible at the limb as glowing arches. Filaments are the same structures seen against the solar disk, where they appear as dark threads against the brighter chromosphere. These structures are all magnetically supported, and they trace the geometry of the magnetic field in the lower solar atmosphere with a directness and beauty that makes solar images from chromospheric wavelengths among the most striking in all of astronomy. And then there is the corona. The corona is the sun's outer atmosphere, extending from the upper chromosphere outward for millions of kilometers into interplanetary space. It is ordinarily invisible, overwhelmed by the brightness of the photosphere, even at small angular separations from the sun's disk. But during a total solar eclipse, when the moon's apparent disk precisely matches the sun's apparent disk and blocks the photospheric light, the corona becomes visible to the naked eye as a pearly, luminous halo surrounding the moon's black silhouette. It is structured by the sun's magnetic field into rays, streamers, helmet structures, and plumes, a complex, three-dimensional architecture of magnetic flux tubes filled with thin, hot, coronal plasma. The corona is hot, extraordinarily hot. Measurements of the corona's emission in X-ray wavelengths, first confirmed in the 1940s and refined continuously since, revealed temperatures between 1 million and 3 million Kelvin. In some regions, during periods of high solar activity, local temperatures can exceed 10 million Kelvin. The photosphere below it is about 5,778 Kelvin. By any intuition about heat transfer, heat flows from hot to cold, not cold to hot. This is deeply puzzling. Something must be delivering energy to the corona from the cooler photosphere and chromosphere below. What is that something? This is the coronal heating problem, and it has been open since the 1940s. Arthur Eddington, the British astrophysicist at Cambridge, whose 1919 observations during a total solar eclipse confirmed Einstein's general theory of relativity by measuring the deflection of starlight by the sun's gravity, described the problem of the solar interior as one of the central challenges of astrophysics. The coronal heating problem, identified shortly before Eddington's death in 1944, would have been a worthy successor to his attention. It combines beautiful physics, complex observations, and a resistance to simple explanation that has persisted for 8 decades. The two leading proposed mechanisms are wave heating and nanoflare heating. Wave heating invokes Alf-Vén waves, oscillations that propagate along magnetic field lines in the corona, carrying energy upward from the photosphere where they are generated by convective motions jostling the footpoints of coronal magnetic field lines. When Alf-Vén waves dissipate in the corona, through various mechanisms, including wave mode conversion and turbulent cascades, they deposit energy as heat in the coronal plasma. Nanoflare heating, proposed by Eugene Parker at the University of Chicago in 1988, invokes tiny explosive events, individual magnetic field line reconnection events releasing energies of roughly 10 to the 17th joules each, occurring throughout the corona at a rate sufficient that their cumulative effect maintains the observed coronal temperature. No individual nanoflare has been directly observed with current instruments, but the statistical signatures of their occurrence are growing clearer. Both mechanisms are real. Both almost certainly contribute. The question of their relative importance and whether there are other mechanisms still unidentified is what remains unsettled. Eugene Parker's name carries particular weight in solar physics. In 1958, Parker predicted, against the objections of colleagues and journal reviewers who recommended his paper be rejected, that the sun must have a constant outflow of charged particles streaming from its corona into interplanetary space. He called it the solar wind. The prediction was controversial. The prevailing view was that space between the planets was effectively empty, or at most filled with a thin static gas in approximate equilibrium. Parker's analysis of the corona's pressure at large distances showed it could not be in static equilibrium. The pressure at large distances required a supersonic outflow to be self-consistent. The physics demanded a wind. Within a few years of the paper's publication, direct measurements by spacecraft had confirmed the solar wind's existence and basic properties. The Parker Solar Probe, launched by NASA in August 2018, bears Parker's name and represents the most ambitious direct investigation of the solar wind and corona ever attempted. Flying to within approximately 6.2 million kilometers of the Sun's surface, inside the orbit of Mercury, deep inside the corona, far closer than any spacecraft had previously ventured. The probe measures the solar wind plasma, magnetic field, and energetic particles in the region where the solar wind originates and is accelerated. Its findings have produced surprises that are still being processed. The solar wind near the Sun is far more structured and turbulent than models predicted, featuring rapid large-amplitude magnetic field reversals called switchbacks that may play a role in accelerating the solar wind and depositing energy in the corona. The Alfvén's surface, the boundary beyond which the solar wind is faster than the Alfvén waves propagating through it, the point at which the solar wind truly decouples from the sun and becomes a free-flowing outward stream, was identified from Parker probe data in 2021. Confirming that the probe was already flying within a region of the corona closer to the sun than the solar wind's birthplace. Eugene Parker died in March 2022 at the age of 94. He had lived to see his spacecraft reach the sun. He had seen the solar wind prediction that nearly wasn't published become the cornerstone of heliospheric science. The coronal heating problem he contributed to framing with his nanoflare theory remains open. But it is being approached from the inside now, with instruments he helped inspire in ways not possible when he first proposed the idea. Let that settle without urgency. The corona continues, the probe continues, the mystery remains, and the investigation is alive. Before we step from the corona into the territory of what remains unknown, it is worth dwelling briefly on two of the most energetic phenomena the corona produces: solar flares and coronal mass ejections. These are not merely dramatic visual events. They are the primary ways in which the sun's internal energy reaches the Earth's environment in forms other than steady warmth and light. A solar flare is a sudden, explosive release of energy in the corona, driven by the rapid reconnection of stressed magnetic field lines in an active region. When the magnetic field configuration in a sunspot group becomes sufficiently twisted and tangled, as the footpoints of the field lines are shuffled about by convective motions in the photosphere below, the field stores energy like a coiled spring. At some threshold of complexity, the field undergoes a rapid simplification. Field lines of opposite polarity snap together and reconnect, releasing their stored magnetic energy in a burst that accelerates electrons and protons to near-light speeds, heats local plasma to temperatures of tens of millions of Kelvin, and emits radiation across the entire electromagnetic spectrum simultaneously, from long radio waves to hard X-rays and gamma rays. The largest solar flares release energies on the order of 10 to the 25th power joules, roughly equivalent to 1 billion thermonuclear bombs detonating simultaneously, though spread across minutes rather than microseconds. Closely associated with major solar flares are coronal mass ejections, events in which 1 billion or more tons of coronal plasma, threaded with magnetic field, are expelled from the sun at velocities ranging from a few hundred to several thousand kilometers per second. A fast coronal mass ejection can cross the distance between the sun and Earth in a day or less. When such an ejection strikes the Earth's magnetosphere, it can induce what are called geomagnetic storms, disturbances in the Earth's magnetic field that drive currents in the ionosphere, amplify the aurora to low latitudes, and in severe cases can induce damaging currents in long electrical conductors on the Earth's surface, including power transmission lines and pipelines. The most powerful geomagnetic storm in recorded history, the Carrington event of September 1859, caused by a massive coronal mass ejection that struck Earth just 17.5 hours after the associated solar flare was observed, disrupted telegraph systems across North America and Europe, set telegraph offices on fire, and produced auroras visible at tropical latitudes. A comparable event today, striking an electrical grid and satellite infrastructure far more extensive and interconnected than anything existing in 1859, would cause disruptions on a scale that planners and engineers take very seriously. Space weather forecasting, the ability to predict when and whether a coronal mass ejection will strike Earth, and how strong the resulting geomagnetic disturbance will be, is now an active field with direct practical importance, driven by the same need to understand the corona and the solar wind that motivates the Parker Solar Probe and other missions. There is something in the contrast between the gentle and patient imagery of tonight's exploration and the reality of what the sun occasionally does: billion bomb flares, billion-ton plasma clouds, geomagnetic storms, that is worth acknowledging honestly. The sun is not only a source of gentle warmth and light. It is a magnetically active star, and its activity, while not existentially threatening to life on Earth under normal circumstances, is not trivial. The same physics that warms your face in the morning can, in its more extreme expressions, darken a continent's electrical grid. The sun is patient and ancient and beautiful. It is also, occasionally, very violent. Tonight, none of its violence is directed at you. The auroras are quiet. The grid is on. The sun is simply burning, and that is enough. The solar wind that flows outward from the corona is not uniform. It has structure. There is a slow component flowing at roughly 300 to 500 kilometers per second, which originates primarily from the boundaries of large magnetically closed regions called helmet streamers, the bright, elongated coronal structures visible during eclipses. And there is a fast component flowing at 600 to 800 kilometers per second, which originates from coronal holes, regions where the magnetic field lines point outward into space rather than looping back to the sun, allowing plasma to escape freely. The polar regions of the sun, where large coronal holes are common, are the source of much of the fast solar wind. As the fast and slow components of the solar wind flow outward together, they interact where they meet, the fast wind running into slower-moving material ahead of it, creating compressed regions called correlating interaction regions that produce their own energetic particles and magnetic field enhancements. The inner solar system is threaded with these structures, rotating with the sun like a sprinkler pattern, sweeping past the Earth approximately every 27 days as the sun rotates. The Earth's magnetosphere shields us from direct contact with the solar wind plasma, but the pressure fluctuations and magnetic variations in the passing solar wind drive the auroras, modulate the radiation belts, and affect satellite operations in low Earth orbit. When the Parker Solar Probe dives through the inner corona, it is traveling through the birthplace of all of this structure. The measurements it returns of magnetic field switchbacks, of suprathermal electrons, of the precise velocity and density profiles of the nascent solar wind, are being used to test and constrain the competing theories of solar wind acceleration and coronal heating in ways that will take years to fully interpret. The picture of the corona we have tonight is sharper than it was a decade ago, and it will be sharper still a decade from now. There is something specifically moving about the Parker Solar Probe's existence as a piece of human engineering. It was conceived in the 1950s as a theoretical possibility, a spacecraft that could dive close enough to the sun to sample the corona directly. It took 60 years to become technically feasible. It was named after Eugene Parker, while he was still alive to know it, as a recognition that the solar wind he predicted and the corona he helped to theorize were, finally, being visited. The spacecraft has a heat shield built from carbon composite foam sandwiched between carbon fiber face sheets, engineered to survive temperature swings between 1,400 degrees on the sun-facing side and negative 200 degrees on the shaded side, while the scientific instruments behind it operate at room temperature. It navigates using Venus flybys to gradually lower its orbit, sacrificing orbital energy at each pass to fall closer and closer to the sun on successive perihelion passes. None of this is something the sun asked for, or needs, or notices. But we built it anyway. We sent it there anyway, because the corona heats itself to millions of degrees, and we do not know why, and we would like to know. That impulse, to look more closely, to understand more deeply, to send a machine the size of a car to within 6 million kilometers of the surface of the nearest star, is, in its way, one of the finest things about us. What we still don't know, and why the not knowing is part of the picture. It would be easy to come away from this long, patient survey with the impression that the sun is understood, cataloged, its physics established, its interior mapped by a century of theory and observation. This would be wrong in an important way. The sun is not a closed chapter. It is an active investigation. The same star that inspired ancient myth, that drove the first systematic astronomical observations, that provided the first laboratory for nuclear physics and general relativity, continues to surprise the scientists who study it most carefully. The coronal heating problem has been described. 80 years open. Two main mechanisms proposed. The balance between them unresolved. Additional mechanisms possible. Parker's solar probe is providing constraints that could not exist before, but the problem is not yet solved. The solar cycle is another honest uncertainty. We can describe the 11-year periodicity. We can explain the broad mechanism of magnetic winding, amplification, and surface emergence. But we cannot reliably predict the amplitude of future cycles. Whether the next maximum will be quiet or intense. Whether a prolonged suppression of activity like the Maunder minimum of 1645 to 1715 might recur. Whether the cycle length will vary. These are questions for which current models provide only probabilistic guidance rather than firm predictions. The Maunder minimum, a 70-year period during which sunspot activity nearly ceased entirely, coinciding with the coldest decades of the Little Ice Age in Europe, demonstrates that the solar cycle is not fixed and that departures from the normal pattern can have consequences that reach all the way to the surface of the Earth. Why it occurred, and whether we could recognize the onset of a similar episode in advance, is not yet understood. The deep radiative zone remains the least directly observed region of the solar interior. Helioseismology is most sensitive to the outer portions of the Sun, and the deep radiative zone is inferred with lower precision than the convective zone. The three-dimensional structure of the tachocline, the thin shear layer where so much of the Sun's magnetic behavior is generated, is not directly observable. The precise mechanism by which the toroidal magnetic field built up at the tachocline rises through the convective zone and emerges at the surface as active regions is an area of ongoing modeling and simulation. There is also what is called the solar abundance problem, a tension between two independent ways of determining the chemical composition of the Sun. Spectroscopic analysis of the Sun's surface layers, revised using improved models of solar atmospheric physics in the early 2000s, suggests a somewhat lower abundance of oxygen, carbon, and neon than older measurements indicated. But helioseismic observations, which probe the Sun's interior through its oscillations and are sensitive to the composition-dependent sound speed profile, are in better agreement with the older, higher abundance estimates. The two methods give discrepant answers, and neither can be simply dismissed. The discrepancy is not large in percentage terms, but it is significant for detailed solar models, and its resolution, whether through improvements in spectroscopic modeling, in opacity calculations, in helioseismic techniques, or through the discovery of some missing physics, is actively sought. And there is the faint young sun paradox, which connects the history of the Sun to the history of life on Earth. The Sun was roughly 70% as luminous 4.6 billion years ago as it is today, as a consequence of the gradual accumulation of helium in the core, increasing the core temperature and fusion rate over time. This means the early Earth should have received substantially less solar energy than today, enough less that by simple calculations, the early oceans should have been frozen solid. Yet geological evidence shows liquid water, active weathering, and what appears to have been a relatively mild climate as far back as 4 billion years ago. Something kept the early Earth warm despite a dimmer sun. Whether a different atmospheric composition rich in greenhouse gases, a different cloud cover, a different albedo, or some combination of factors, but the precise resolution of the paradox is still debated. The portrait of the Sun given in tonight's exploration is accurate in its broad outlines and faithful to the specific facts named. But what gives it real depth is the recognition that the portrait is unfinished. The questions that remain open are not failures of understanding. They are the shape of the frontier, the solar cycle, the corona, the dynamo, the tachocline, the faint young sun. These are places where the science is still moving, where new data arrives from new instruments and old models are revised, and surprising results emerge from data collected by spacecraft flying closer to the Sun than Mercury's orbit. The Sun has been doing what it does for 4.6 billion years in complete indifference to our attempts to understand it. The fusion reactions in the core do not require our models to be complete. The photons wandering through the radiative zone do not wait for us to refine the opacity calculations. The corona heats itself by whatever mechanism it actually uses, regardless of which of our proposed explanations proves most accurate. There is also an entire frontier connected to what the sun can tell us about stars more generally. The sun is the only star we can study in anything like the detail applied to a laboratory specimen. Every other star is a point of light, its properties inferred from its brightness, spectrum, and variability. The sun, up close, resolved in exquisite detail, probed by spacecraft, measured in oscillations and neutrino fluxes and magnetic field maps, is effectively a Rosetta Stone for stellar physics. The degree to which our models of the sun's interior are accurate directly determines the reliability of our models of every other star, and by extension our understanding of stellar evolution, galactic chemistry, and the abundance of elements throughout the universe. The carbon and oxygen in your body were forged in the cores of stars that lived and died before the sun was born. The iron in your blood was produced in a supernova explosion billions of years ago. Our understanding of these nucleosynthesis processes, of how heavy elements were built up over cosmic time in stellar interiors and explosive deaths, depends on our models of stellar structure and evolution, which are anchored in and validated against our understanding of the sun. Uncertainties in the solar models propagate outward into uncertainties in our understanding of everything from the age of globular clusters to the chemical history of the Milky Way galaxy. The sun is, in this sense, not just interesting in itself. It is the calibration point for a very large portion of astrophysics. When John Bacall spent decades insisting that the solar models were correct and that the neutrino problem lay with the neutrinos themselves, he was defending not only a model of the sun, but a framework for stellar physics that underlies much of our understanding of the cosmos. He was right. The framework held. The cosmos matched the model. But frameworks can always be refined. The solar abundance problem, the details of the tachocline, the mechanism of coronal heating, the long-term behavior of the solar cycle, each of these, when resolved, will not only improve our understanding of the sun, it will improve our models of every sun-like star we observe, and by extension, the inferences we draw from those stars about the age, history, and evolution of the universe. The sun, the nearest star, the oldest companion of life on Earth, is still teaching us things. It will continue to do so, patiently, for as long as we are here to observe it. And long after we are gone, it will continue doing exactly what it has always done, fusing hydrogen in its core, moving energy slowly through its radiative zone, churning in its convective zone, sending its light across 150 million kilometers of empty space toward a small blue planet that, for a brief time, looked back. The portrait is not yet finished. It does not need to be finished tonight. There is also what it means that the sun is the nearest star, and therefore the only star we can study with anything approaching the detail of a laboratory specimen. Every other star in the universe is a point of light, its properties inferred from brightness, spectrum, and variability, with no hope of direct surface imaging or interior probing by spacecraft. The sun is the exception. What we understand about stellar physics, how stars form, how they burn, how they age, how they die, how they produce and distribute the heavy elements that make planets and life possible, is anchored in and validated against our understanding of this one specific star, 150 million kilometers away. The carbon and oxygen in your body were forged in the cores of stars that lived and died before the sun was born. The iron in your blood was produced in a supernova explosion billions of years ago. Our understanding of these processes, of stellar nucleosynthesis, the building of heavy elements in stellar interiors and explosive deaths, rests on stellar models calibrated against solar observations. When Bacall insisted that the solar models were right and the neutrinos were doing something unexpected, he was defending not just a model of one star, but the credibility of an entire framework for how stars work, and therefore how the universe became chemically complex enough to allow life. The framework held. It continues to hold, too. And every improvement in our understanding of the sun, every refinement of the opacity tables, every helioseismic inversion revealing a new detail of the radiative zone, every Parker solar probe result constraining the corona, propagates outward into sharper models of every other star we observe, and sharper understanding of everything those stars have built and distributed across the galaxy. We are, in a very direct sense, made of the sun's predecessors, and we are learning about those predecessors by studying the sun. And so we let the sun rest in mind, not as a symbol, not as a metaphor, but as a fact. A sphere of plasma 696,000 kilometers in radius, sitting right now 150 million kilometers from you, converting 620 million tons of hydrogen into helium every second, releasing 3 million tons of matter as pure energy every second, sending neutrinos outward at the speed of light, 65 billion of them passing through every square centimeter of your body right now, and photons outward on a 100,000-year journey, maintaining in quiet, ancient equilibrium the conditions that every living thing on this planet depends upon. Everything we have explored tonight is happening right now. Protons are tunneling through the Coulomb barrier in the core. Photons born in fusion reactions that occurred when early humans were crossing land bridges between continents are now approaching the photosphere after tens of thousands of years of wandering. 4 million granules, each the size of Texas, are rising and sinking and dissolving and reforming on the sun's surface. The magnetic field wound in the tachocline is building slowly toward whatever the next solar maximum will bring. The corona is being heated by mechanisms not yet fully understood, and the solar wind is flowing outward at 400 to 800 kilometers per second through the solar system, past the Earth, past Jupiter, past the outer planets, all the way to the heliopause, the boundary between the sun's influence and the interstellar medium, more than 100 astronomical units away. Think, for a moment, of what it means that the energy warming you tonight has been in transit for 100,000 years. It was produced in a nuclear reaction in the solar core at a time when anatomically modern humans were still sharing the Earth with Neanderthals, when the climate was deep in a glacial cycle, when the shape of the coastlines was different because sea levels stood lower by 100 meters or more. The world in which that energy was created was not the world you inhabit, and yet here it is, arriving tomorrow at your window, passing through the atmosphere, absorbed by your skin, converted to heat, warming you as it has been warming every living thing on this planet for every morning since the first morning there were living things. The energy that will warm the Earth next century was produced in the solar core roughly 70,000 years ago. The energy that will warm whatever civilization or form of life exists in 10,000 years, whatever shape humanity takes, or whatever comes after, is being produced right now at 15 million degrees in the center of the nearest star. None of this is metaphor. All of it is physics, and all of it is happening right now while you are still. None of this stops. None of it pauses. None of it asks anything of us. Let your breathing slow. Let the picture of the sun's interior settle in the way that vast and ancient things settle, without urgency, without demand, without the need for an audience. The radiative zone is dark and patient, as it has always been, as it will always be for another 5 billion years. The convective zone is rising and sinking. The corona spreads its thin, hot light into the dark of the solar system. The neutrinos stream outward, and through you, and through the floor, and through the Earth, and out the other side, and onward toward the stars. Let the day's concerns fold away. Let the distance between you and the solar core, 696,000 kilometers of plasma and mystery and slow fire, remain exactly what it is. Something so far away and so ancient and so vast asks nothing of you except that you continue to exist in its warmth, to live briefly in the light it prepared for you over 100,000 years ago and sent.